DuckDB under the hood, Module 10, Vectorization Deep Dive. A scalar add takes 1 cycle to combine 2 numbers. A SIMD add takes 1 cycle to combine 8 pairs of numbers. Same instruction, 8 times the work. Watch the lanes light up. In the last module, you saw how DuckDB splits a query into pipelines and runs them in parallel across threads. Each thread runs the same vectorized inner loop. Today we go down one more layer, into the loop itself. DuckDB processes rows in batches called vectors. The default batch is 2048 values. That number is not arbitrary. It is just small enough to fit inside the CPU's level 1 cache, and just large enough to amortize the per call overhead of running an operator. By the end of this module, you will know exactly why 2048, exactly why SIMD lanes matter, and exactly why some queries hit the wrong predicate and stall on every row. DuckDB under the hood, Module 10, Vectorization Deep Dive. A vector in DuckDB is a small batch of rows for a single column. The default size is 2048 values. Operators consume vectors and produce vectors. Never one row, never one full column. Why this size? 3 constraints meet here. A vector of 2048 doubles fits inside level 1 cache, so the inner loop never waits on RAM. The number is divisible by every common SIMD lane width, 4, 8, 16, 32. So the compiler can unroll cleanly. And the per call overhead of running an operator amortizes over enough rows that it disappears. Push the size up to 8000 and the working set spills out of cache. Drop it down to 256 and per call setup dominates. 2048 is the sweet spot. SIMD stands for single instruction, multiple data. Modern CPUs have wide registers, 256 bits, sometimes 512. And instructions that apply one operation across all the lanes at once. A scalar add operates on one value and finishes in a cycle. The corresponding 8-lane SIMD add operates on 8 values and finishes in the same cycle. The instruction takes the same time. You just got 8 times the work. DuckDB does not write SIMD intrinsics by hand. It writes plain inner loops over vectors and lets the compiler auto-vectorize them. A vector of 2048 doubles compiles into about 256 SIMD instructions on a modern chip. That is one tight inner loop saturating every execution unit on the core. Every if statement is a branch. The CPU guesses the outcome before the comparison finishes, and when the guess is wrong, it flushes the pipeline. Each misprediction costs 10 to 20 cycles. When the predicate is predictable, the cost is 0. Sorted data, all true filters, all false filters. The predictor is right every time. 50% selectivity on random data is the worst case. The CPU is wrong half the time every time. DuckDB's vectorized predicates avoid this entirely by using branch-free code. The loop always runs, no conditional jump, nothing to mispredict. Same result, none of the cost. Here is what that looks like measured. The branchless version runs at constant time regardless of how many rows pass the filter. The branchy version peaks at 50% selectivity, exactly where the predictor is wrong half the time. That gap is the misprediction tax DuckDB's vectorized predicates eliminate. Modern CPUs include a hardware prefetcher that watches your memory access pattern. Read addresses sequentially and it pulls the next cache lines in before the program asks for them. Reads land in cache. Memory bandwidth saturates. Random access breaks this. Every jump to a fresh address means the prefetcher guesses wrong and the CPU must wait while main memory sends the value, about 100 nanoseconds per stall. That is the hidden cost of reading a wide row when you only need 2 columns. Columnar storage eliminates this. Adjacent values in a column sit at adjacent addresses. A scan reads them in order. The prefetcher runs ahead and memory bandwidth is fully used. Here is the measured gap. A sequential scan reads at full memory bandwidth. A random scan stalls on every fetch, 88 times slower in this benchmark. That is what columnar storage and vectors of 2048 contiguous values buy you. We attach the TPCH scale factor 1 database and switch to it. 6 million rows in Linitem, 5 columns we will touch in the next query. Now we are ready to run the workhorse aggregation, the same shape as TPCHQ1. Here is a filter, a multiplication, and a group by over 6 million rows. We run explain analyze and watch the timings. The bottom of the plan is the sequential scan. That is the inner loop running on vectors of 2048 rows at a time, applying the date filter as it goes. Most of the wall clock sits here because this is where memory bandwidth lives. Above the scan, the projection computes extended price times 1 minus discount. That is the CMD path 8 lanes wide and nearly free in wall clock terms. At the top, the hash group by maintains 3 running totals, 1 per return flag, 3 groups in, 3 rows out, also nearly free. The arithmetic and the aggregate cost almost nothing. That is what vectorized execution buys you. Your turn. Vector size in DuckDB is a compile time constant. You cannot change it from SQL. To do this exercise live, install 2 binaries side by side, one built with vector size 512 and one built with vector size 8192, and time the same aggregate on each. If you only have the default binary, run the included Python harness. It sweeps batch sizes from 64 to 65,536 and shows the same curve. Predict whether smaller will be faster, then check. Predict whether bigger will be faster, then check. The exercise file has the prediction table. Welcome back. Let us walk the same query at the default vector size and read the operator costs. The sequential scan dominates wall clock, that is memory bandwidth, the floor of any aggregate over 6 million rows. The projection is nearly free because it compiles into one tight CMD loop. The hash group by is also nearly free because 3 groups fit inside 2 registers. At vector size 512, the hash group by takes a much larger share of wall clock. Per call setup becomes visible because each call processes 1/4 as many rows. At vector size 8192, the scan slows down measurably. The working set no longer fits in level 1, and every read costs 1 hop further out in the cache hierarchy. The default of 2048 is the only point on the curve where neither effect is visible. That is why DuckDB picks it. Here is what we covered. A vector is a batch of 2048 column values that fits inside level 1 cache. SIMD lanes let one instruction operate on 4, 8, or 16 values in parallel. Branch prediction makes predictable predicates free and unpredictable predicates costly. 50% selectivity is the worst case. Cache-friendly access reads sequential addresses at memory bandwidth, while random access stalls every time. DuckDB picks 2048 as the sweet spot, small enough for the cache to hold, large enough to amortize per call overhead, divisible by every common CMD width. 3 constraints, 1 number. Next up, module 11, the optimizer.